All right, I guess we get started. Okay. So yesterday we looked, we had a lot of definitions and overview of how we were going to set up our general calculation of leading order amplitudes. Today we're going to actually start doing something and start calculating some leading order amplitudes, which is more fun. So the idea is we want to know we're going to calculate an arbitrary matrix element at leading order, because that's what I promised was in the heart of modern generators, is some ability to calculate any process you like. So you want to have some means of not having to have some matrix element for a specific process, but an ability to calculate them on the fly from your knowledge of the underlying theory. So there's two ways that the modern generators would do a recursion relation. So we'll see that solving a recursion relation is the way you do this. So you just build up successively more complicated amplitudes from smaller sub-amplitudes that you know. Now there's two ways you can go about doing this recursion, either on or off shell. And what this means is whether all your particles are on shell, which is the one that we'll talk about today, or whether you keep one particle off shell, which is the Brenzgila recursion relation, which is a bit older. And actually, if I was being 100% honest, which I hate to be, then I would say the Brenzgila recursion relation is used more because it's a bit, by being off shell, it's a bit more generic. You don't have to worry so much about massless particles and all that sort of thing. But the on-shell recursion relations are just mathematically so much more beautiful. So as we're in TASI, the theory is the first thing in the title. We'll do Bcfw because it's just nicer. So slightly less useful, but much more mathematically appealing. So that's what we'll look at today. So we're going to look at on-shell recursion. And these are called the Bcfw recursion relations. And so this stands for Brito, Cacciazzo, Feng, and Witten. So the original paper in which the relationship was proposed was by BCF, and then there was a second paper a couple of months later, which included Witten, and that proved why this thing worked in generality. So this proof paper is now what they're referred to as the Bcfw recursion relations. And the proof paper is really nice. Right? It's like a few pages. All it needs is complex analysis, and then some simple complex analysis we'll go through today, and then you understand it. And what's amazing is that this was done not that long ago. Right? This is just as tree level. You think, there's nothing we're ever going to learn interesting about tree level. In field theory, we've just known that for donkey's years, so there can't be anything interesting to discover. But this discovery was 2006, I think, 2005, and completely revolutionized essentially both tree and loop level understanding, because it allowed us to calculate, understand gauge theory in a way we didn't before, and when applied to a whole bunch of different theories, not just the standard model, it led to a lot of interesting results. So the message here is that it's actually it's nice to see that even things as a mundane as a tree level scattering amplitude can sometimes lead to new insights, even nowadays. So anyway, that's the motivation. All right, so what we're going to use a bit of complex analysis, and we're going to use the universal factorization of tree level amplitudes, and we'll come to that in a minute, but we'll start with just a bit of complex analysis. So what we're going to do is imagine that we have some endpoint amplitude. So it's got lots of massless legs sticking out of it, all the way around to n. And somewhere in our ordering, this is a color ordered amplitude, so somewhere in our ordering there's two legs, I and j. Now we're going to make those legs be preferential. We're going to treat them as special. They need not be adjacent, even though they are alphabetically. They do not have to be adjacent in the color ordering, so it could be 2 and 6. You can just choose whichever two you like. So you choose two legs for special treatment. So they're special. All the other legs get a participation trophy. All right. Now what do we do with this special? Apart from giving them an increased ego, we're going to do something mathematical. So we're going to say we take pi, and we'll replace it by the original vector, and then we're going to add on this funny object here. Okay. So this thing here is so we're shifting pi, so it goes to the original vector plus z. So I've spoken with other lecturers, and we've decided that English is going to win, so it's going to be z. So z over 2, and the 2 is important. And this thing here is another vector, which is not a real Minkowski vector. It's made out of the square bracket of I and then the angle bracket of j. Okay, so that's not necessarily that usual. Am I getting a bit bored? All right. And then pj we're going to also shift. All right. Now it's late in the day and you've been working hard all day, but hopefully it's not too hard to see that if I add these two vectors together, they cancel, right? Here's a positive sign, here's a minus sign. What does that mean? That means that now in the shifted momentum, so P, I, Z, my new one, P, I, Z, and the new one, P, J, Z, the sum of the two is just equal to the sum of the unshifted momentum. So it's a bit notationally confusing. But what this is telling me is that the Z dependence cancels out in the sum. Right? So it's okay. Why is that good? Well, that's good because we haven't broken momentum conservation with this shift. So overall momentum conservation is still there. And that makes us happy. Okay, good. So we still have overall momentum conservation. Now what else do we have that we like? Well, let's square one of these things up. So if I take pi, put a hat over it now to indicate that this is the shifted momentum. So if I square that, then what do I get? So I get pi squared, which is 0. And then I'm going to the top line, I'm going to get plus 2, then a half, so that gives me z. Then I get j, I, and then I get z squared over 4, j, gamma mu, I, j, gamma mu, I. And we remember from our spinor introduction yesterday that if I have the same spinor product, so this thing here is equal to 0, which we can see either from the helicity, the projection operators, or just from the fact that it's anti-symmetric in the two indices. So that's by definition that has to then vanish if I repeat the indice. Second term. No, I've contracted it through, right? So this thing here is an I slash, if you like. Right, but we don't normally put the slash in because it's hard enough to understand the notation anyway. Good. All right. So anyway, so this thing, it doesn't matter what we're debating, whether there should be anything in there, because this thing is 0. This thing is 0. And this thing here, remember, then we contract the angles together, so we get JJ, I, which is also 0. So this whole nonsense here is, in fact, 0. Good. So what is this telling us then? This is telling us that this new direction, this z-dependent pi, is also still light-like, and overall momentum is conserved. So what we have is essentially now still an amplitude. It's not the physical amplitude anymore, but it still has on-shell final states, and it still has momentum conservation. So it behaves very much like a regular old physical amplitude. The major difference is that we've lost conjugation. So when I do a conjugation on this vector here, I don't get back something which makes it a real vector. So now this is a complex momentum. So pi hat and pj hat are complex vectors. Okay. So this thing here, so this amplitude now, an z, is now a complex function. Right? So we've taken our physical scattering amplitude, we've rewritten it in terms of these new momentum, which now depend on z, and now we have a complex function which we call anz. Okay? Everyone's happy so far? Cool. All right. So, okay, so now my next bold claim is that A and Z only has simple poles. And why is this a bold claim? You may have guessed quite legitimately that it should have double poles, because my tree level amplitude is going to be a function of propagators. Propagators are naturally quadratic, so I should get quadratic dependence on Z and then have double poles. So it sounds very sensible that we should have double poles, but now I'm going to show you that doesn't happen. Okay? So why do we only get single poles? Well, so we'll choose a subset of external momentum. So it goes from alpha ending on beta. And this is some subset of my blob over there. So a subset of external states. Now, I have two options. I have either none of I and j are in this set, or one of them is in this set, or both. Right? So I have three options. So if neither I nor j in the set, then P, capital P alpha beta, which is just the sum of all of the terms in there, doesn't depend on Z. So there's no poles. Okay? All right, that's the first option if I didn't have any of them in there. Now, if I had both, then I still don't have any poles, because P alpha beta as a function of Z is just P alpha plus somewhere there's Pi as a function of Z, somewhere else there's Pj as a function of Z, and then it ends with P beta. Now we saw over there that momentum is conserved, so this thing here is just the same as Pi plus Pj, and so accordingly this thing doesn't depend on Z either, so no poles. Okay, so we're killing poles left, right, and center. Okay, so that now gives me one other option where I choose one of them. So we say if I is in the set but not j, now we really do get a Z dependence, so we have to be careful. So I'll call it P hat, which means it depends on Z. So I get the original vector, and then I get my correction, which I added on, which is this term up there, plus Z over 2 J gamma mu I. All right. So this is our suspicious term. We're going to square this up, and we're going to think there's going to be a double pole. But already, for the same reason why this thing remains light-like, you see there isn't going to be a double pole, because when I square this thing here, I just get the thing at the very top. I might even get my laser pen. It's nothing like a light show. Cool. All right. Yeah, we have this thing here. Is the same thing as when I square it up. I'm going to this one is going to go like that, which is 0. So so there isn't any quadratic term, and in fact I can work out what the square of it is. So P hat squared alpha beta is just going to be the unshifted Minkowski product plus a correction that goes like Z Z J P alpha beta I. And so there's only single poles because it just depends linearly on Z or Z. Sure?
So now you are arguing that if the subset of the alpha beta, you calculate the p mu, which is sum over all the momentums in the set in the subset.
Yeah.
Which I think you mean you want to run into the propagator, and that's the momentum in the propagator.
Yes, this is the momentum of the propagator. So
potentially can give a pole.
Yes.
You are checking with the people.
yes.
But that does not necessarily mean that subset is for the external momentums. Right?
So when so I have my big blob, 1 to n. Now this thing is a tree level structure. So the only time it can have a pole is if a propagator blows up, right?
Yes.
So then I can classify all the propagators by looking at all pairings of external momentum, because ultimately there's no unresolved propagator which will be a loop. All my propagators are sums of external momentum at tree level, right?
Yes.
So all my propagators. So then I have the question of is one of my shifted legs in the sum or not? Right? Is that clear?
Yeah, but for example, you have 3 legs on the left side and 1 propagator and 3 on the right hand side.
Like this?
You make it 2 is okay. But if you said, yeah, if you order 1, 2, 3, and 3, 4, 5.
Mm-hmm.
So if you choose, you complexize the 4 and 5.
Yes.
And then you choose 1, 2, 3. Oh, sorry.
So then P123 doesn't depend on Z. P45 doesn't depend on Z.
Yeah, but the propagator I think is, for example, is 3, 4, 5 in the...
The propagator here is P345, yes, or P12, depending on how you want to call it. But it doesn't depend on Z. I guess I don't see the question.
Oh, so you said the P alpha beta is all the possible...
P alpha beta is just some generic combination. You can just choose. There's nothing special about alpha and beta.
Not some of all the...
No. It's not. It's just you're choosing some subset. And now we're just looking at the types of structure we expect at the moment. And we've seen that there's basically going to be 2 types of structure. One which doesn't depend on Z at all, which is when both the shifted legs are on the same side, and then one which does depend on Z linearly, when I have one on either side. Perfect. Good. All right. So we've seen that our propagator, if it depends on Z, can only depend on Z linearly, and then we can solve for the type of Z that we're going to get. P hat squared. What am I doing? I want this to vanish, so this is just a regular P squared divided by So these are the types of residue pole I would expect, right? They occur when this thing would equal 0. Okay, good. Everyone still happy? All right. So now the question is, what can we say about these types of poles here? So we know that we have to, as we were just talking about, we know we have to have a propagator that blows up. And what happens when this thing blows up is that the propagator is going to infinity, and that's going to infinity because this internal, so here I've chosen a 3-point example, so this thing is going to, SI hat k is going to 0, which means the propagator goes to infinity, and then what that's telling us then is that this intermediate leg is going on shell, right? Because SI hat k equaling 0 is telling me that this is now becoming an on-shell particle. So that's nice, because then it looks like I have an amplitude on either side. But we have a couple more steps to get to there first. All right, so now we want to we want to write our A n of z completely generically. So we're going to go for some Laurent series. So we know there's a whole bunch of simple poles, and then there's going to be some finite bits, which I can write as some series in z. K is equal to 0 to m. Now, m is some power. It's going to be finite because my amplitude is only going to depend on my spinors to some power. So when I shift them, I'm going to have some maximal polynomial dependence I could get. And that's then now what my function is going to look like in general, right, for an arbitrary shift. To m, I mean m, it depends on which shift I choose. It's just this is some non-infinite value, right? Okay, now I would prefer if this thing didn't exist, So let's choose a shift such that dk is equal to 0, which tells me that an of z goes to 0 as z goes to infinity. I would very, very much like to choose this shift. That would make me very happy. Now, in general, certainly for gluon scattering, you can prove exactly which shifts will work universally, but this is not guaranteed, right? This is you can't. There are some shifts that will induce a large z behavior, but for now, we're just going to assume that we did a good shift and that we don't have any large z behavior, which means that all these terms vanish. Okay?
Sorry, quick question.
Yes.
Like there you saw for Z, right?
Yes, Z. Yes.
Isn't p squared equal to 0?
No, p squared is some like some of the other ones, right? So the p squared will be the ones I and k on my I hat and k hat on my left-hand side. So p squared here is the sorry, I should be clear. P squared is the unshifted guy because it hasn't got a hat on it. So p squared is just I k without a hat on I. So p hat squared is going to 0 when this thing blows up, and that's how I solve it, right? So I have this one and this one. This one vanishes, this one doesn't. Okay, good question. Somewhere else. Yes?
The summation of simple poles, to get that, you have to assume that only one gluon can possibly go on shell at a time?
Yes, because how would I... well, no, because they're going to get a recursion relation in the end. So I can sum over... For what would happen if I had another one? Then I would have a second topology here, right? But that's, in the end, I'm going to set them all up into one big amplitude. Also, these things, for tree level, these things are always going to be unique, right? Some subset of these gives me a pole here. It never repeats itself, right? Because there's only one possible way of giving me that momentum conservation. So there is going to be lots of different poles, which is why I sum over them. But there's only one. Yeah, because if I tried to make some other subset in here be on shell, then I couldn't do it simultaneously, right? So if I had, because I only have one shift, right? So I can only go on shell one specific z value blows it up, and then that one will blow up this sum of the whole, but it won't blow up any subsets. All right. More questions?
When you sum over the I, the these that I poles,
Yes.
are the I's all of the legs that are in the alpha to beta set?
These are all possible residues. So any diagram that we can draw that says non-zero that gives us a residue of this form that will couple to non-zero subamplitudes. At the moment we haven't actually derived the recursion relation, right? We've just done momentum conservation.
Oh, so the I is just it's a counting index. It's not indicating which leg I.
Yeah, that's just an overabundance of I. So I'm very self-obsessed. I think I'm very important, so I call everything I. All right, good. Yes, so this is just sum over residues. So we just say, and then maybe we're happier. Good. And then, so okay, but what do we want at the end of the day? We don't want to just do complex analysis all of our lives. We'd like to do something that has physical meaning. Let's see if I can send this one up. And bring this one down. So what I would like is to have A of 0, because A of 0 is my physical scattering. When there is no Z or Z, and instead we just have real momentum. All right, so that's what I want to get. Right? Putting just Z is equal to 0 in my formula. So you see I can get the physical amplitude just by knowing all the residues of my complex function. So I just have to determine the residues. And this is what we were inching towards with the questions about whether different subsets can go on shell. Okay, so when we put a leg on shell, this thing becomes a real physical amplitude. Well, still, it becomes a real physical amplitude because it's still got complex momentum, so it's not quite real. But it is a scattering amplitude with momentum conservation and on-shell leg. So it becomes a scattering amplitude that we can calculate for complex momentum. And so does this side too. So both the left and the right are amplitudes. And so all we have to do is then assign the helicities. We don't know what the helicities are because it's an internal degree of freedom. So we just have to sum over the two possible pairings. And we can say that in the limit where a prop goes on shell, we can write that it's some left amplitude with some helicity, as some function of z, times some right amplitude. And this whole thing is still divided by our p squared of z. All right, so this thing is what's making this factorization happen because this thing is blowing up, so this is turning it into an amplitude. And so we want to basically remap this back to our Laurent series, and then we're done. Right, so we're almost there, because all we have to do is write this p squared z in that form, and then we can get Ci. So that's super easy. So we have, basically have the answer already over here. So I want to factor this thing out. So I can say this whole thing is J P I times Z minus Zi. Right, so I factor this thing out here, out front, and then I just use my definition of Zi over here, which is the value that's going to set the residue, and then I'm done because this thing here is exactly what I'm expanding my Laurent series in, so I can identify Ci. So I'm all over the place on the blackboard. I'll just stay here. I can write this thing as Al so I just put the value of Zi into my amplitudes. And then I take my normalization, and that tells me the coefficients. So what, there's one last trick that we normally do, which is that we would realize that this whole thing down here, so this thing times this thing can be written, so now we've got the physical amplitude, so we have the residues. We want the physical amplitude, so we just put z is equal to 0, and we obtain what we want, but the only dependence left on z is coming in from our denominator. So we get that we write the general shifted amplitude as sum over the residues, the sum over the helicities of some left assortments at some particular residue times some right assortments at some particular residue divided by this thing. This whole thing is just p hat squared of z, and so the physical amplitude just occurs at a of 0, where this thing just goes back to the original momentum. So we just put z equals 0 to get the physics amplitude that we want at the end. And this then is just telling us that physical amplitude is given by this. Divided by p squared, where this one isn't the p squared that depends on z, but is the sum of the physical momentum. And that's it. That's the Bcfw recursion relation. So I told you it was just complex analysis, nothing complicated. And so, okay. So what went into it? So we had to assume that the shift didn't induce any large Z behavior. In our example, we'll see a good and a bad shift that does this. And we see that if I keep on applying this sequentially, each of these amplitudes is going to have less legs than the total. So this is telling me if I keep applying it to exhaustion, I'm eventually going to hit always 3 points. Right? So in our stick diagram, there's going to be a leg, this sort of thing, and then all the others. And this one I can start decomposing in terms of other ones. So in the end, I can build the whole amplitude from 3-point vertices. So this is telling me that this quartic coupling is sort of there. I can get all of gluon scattering at tree level just from the 3 vertex on its own. Cool, huh? All right, any questions before we move on to an example? No? Okay. Stunned into silence or boredom. All right, good. So let's do an example. So we'll add. So yesterday we did a nice simple example where we calculated leptons goes to QQ bar. So now we'll add on additional gluon and we'll calculate the amplitude for E plus E minus goes to QQ bar G. Okay. And okay, so we're going to shift the negative helicity quark, so 4, and the gluon 5. Right? And that means now that I have only one diagram, which is given here. The reason I only have one diagram is that I have to have 4 and 5 on opposite sides to get a z-dependent pole. And then there's only one possible way I can make a 3-point vertex is by sticking the other quark with the gluon. And that gives me my only contribution. So that's what I have to calculate. But I haven't actually told you what shift I'm going to do on these 4 and 5, because we realized that I have a choice here, right? Because when I was doing my whole setup, I said I'm going to shift pi, so I say pi goes to pi plus z over 2 j mu I. But I have a freedom in who's I and who's j, right? So I can shift the angle. So what I'm essentially doing here is shifting the angle on I and the square bracket on j, and leaving the other one alone, which is why I break conjugation symmetry. So I have a freedom in who gets their angle shifted and who gets their square shifted. So I could do, let's see, I'll do the right one first. So I could choose to do angle bracket 5 goes to angle bracket 5 plus z 4, and square bracket 4 goes to square bracket 4 minus z 5. So I could do that one, or I could do square bracket 5 goes to square bracket 5 minus z 4, and angle bracket 4 goes to angle bracket 4 plus z 5. Okay? 50-50. All right. Now one of them is going to be an absolute disaster. The other one's going to be spot on. Which one should we choose? Do you think this one's better, or do you think this one's better? Are you gambling?
Why would it be so different? Because I was assuming since we only did the I put on J's in the section, that you get basically equivalent.
Oh yeah, that's.
If it was J was another I.
I mean that's true, right? Because then that's just looking either side of the diagram, right? Yeah. This momentum is the same as that momentum by momentum conservation. So you could focus on this side and call it P35 hat, or you could focus on this side and call it P124 hat. It's the same. So there is a symmetry there. The shift is how you do this. It's basically flipping I and J, right? So I haven't specified who I and J are, and this one is choosing J as 5 and I as 4. This one is choosing the other way around. Right? Now, the reason it's different is because they're different particles, right? And they have different external helicities. So the symmetry is broken not by the difference in shifts, but by the fact that I'm actually doing a physical calculation with definite helicities and definite amplitudes. So there isn't it's not like this is always a bad shift and this one's always a good shift, which is the right way around. This is just for this case, right? And we'll see shortly. So it's the first weirdness that we'll run into from using complex momentum. Okay, so let's say this one. So the reason why this one is the bad one, and we'll see why the reason once we see what the 3-point vertex is. So I should tell you how we're going to calculate it. Oh, I have a fresh blackboard. That's nice. All right, so we need to know the 3-point vertex in QCD for one quark with positive, one with negative, and a positive gluon. So this thing sadly depends on the square brackets. It's nice and simple. And we also need the 4-point amplitude that we calculated yesterday. Uh, 3q plus 4q minus. This one, if we remember, was 2, 4 squared divided by 1, 2, 3, 4. Okay, so these are the amplitudes that we'll need to calculate this scattering. And this one here is the one that's going to tell us the problems. Right? So we're looking at a 3-point vertex, and we have momentum conservation. So we know that P, which one did I shift? 5. So P5 hat plus P3 squared is equal to 0, right, at my residue. And this is telling me that P5 dot P3 is equal to 0. Right? Because P5 squared is equal, P5 hat squared is equal to 0. It's a light-light momentum. P3 squared is equal to 0. It's also light-light momentum. So therefore, the dot product between the two has to vanish. So in spinors, this is telling me that 5, 3 is equal to 0. Okay. So when I choose my shift, one of these is going to be left alone, and one of them is going to shift to have this dependence, right? Depending whether I choose that one or this one. Okay. Now that means that if I'm not careful, I can run into problems, because if I choose this shift here, then I get that this thing has to equal 0, right? Because if I choose the wrong way around, my only possibility is that the square is equal to 0. Let's see how I want to say this right. I don't want to talk myself into a hole. All right, so we want 5 hat 3 is equal to 0, and not 5. All right, because if this one is equal to 0, then our 3-point amplitude here, so I have to obviously, these are wildcards. When I put that in over here, I'm going to get a square bracket 5, 3. If 5 hat 3, if that equals 0, then my whole amplitude is equal to 0, and then my big statement is that this thing here vanishes, right? Which isn't the case. What's happened is if I chose this shift, my shift has large z dependence, and my simple assumption that I can get the whole amplitude from the sum of the residues is invalid, because there's large z behavior which I don't know from just calculating residues. So the shift which would give the inverse of this is bad. So why? Okay. So why do we choose this one to equal 0? So this is okay if we shift this one, right? The good one, because this is some random equation that relates 5 and 4 to 3. So that gives me some freedom. If so, I can have that being 0 not being a problem. If I had that this shift over here, then I would get that 5 and 3 had to be collinear, which is unphysical. So I don't want to have something which is telling me that 5 and 3 themselves have to be collinear. That's bad. I want to at least have a z dependence I can solve for to generate my residue. So this is what I want, and I get this by putting in this shift here, and then I get that 5, 3 minus z 4 3 plus z 4 3 is equal to 0. That's okay. That makes me happy, and I get that 5 3 is not equal to 0. Good. All right. So, okay. So that's the waffling way of saying that we're going to choose this shift here and not this one because it doesn't give us good behavior. All right. So now we can put these things together and calculate our amplitude. So the thing that we want is given by 3 5 hat squared divided by 3 p hat. So this is the left amplitude. Then I get my unshifted propagator, so 3 5 5 3. That's just S 3 5. Then I get my right amplitude, which is 2 4 hat squared divided by 1 2 4 minus p hat. Okay. Now under my shift for angle hat is just equal to 4, and 5 square brackets is equal to 5. So it's trivial for me to put that into this. I just have to remove the hats. And so the only non-trivial dependence I have left is in the p hats. So I join these two up together to make a spinner sandwich, which is delicious. This 3 5 here is going to cancel this one with a sign, and then I get minus 3 5 2 4 squared divided by 4 p hat 3 3 5 1 2. Okay, I'm nearly there. So now I'd have to substitute for p hat, but remember that p hat 3 5 is p 3 5 plus z. And which one did I choose? I chose 4 gamma mu 5. So that's what my p hat looks like. So when I put this into this spinner sandwich, I'm going to get the 4 angle contracting with the 4 angle here. So this thing actually already drops out, and I'm just left with the p35. So this thing here, I can remove the hat and just call it p35. And then I see a 3 and a 3 when I expand this out, and that vanishes again by the Dirac equation. So I'm just left with a 5. And then you see I'm done because I can open this thing up again and cancel this last annoying square, and I get left with the physical amplitude at the end of the day. Which is just given by A5 0 is 2 4 squared 1 2 3 5 5 4. There we go. So what do we remember from yesterday? This one is MHV. That makes sense because we just said it was going to be 2 positives, 2 minuses, and then any number of pluses. So that fits in with what we thought because we just added in one positivistic gluon. So that's good. It's holomorphic as expected, and it's quite nice. So there's an even nicer way we can write this amplitude if we multiply and divide through by 3 4. Why is that nicer? It's got more terms in it, makes us feel like we've done a harder equation.
I only see 3 different numbers in that one, whereas there's 1, 2, 3, and 4.
Yeah, so it's more complicated. So I'm more likely to impress my friends in the elevator when I tell them I did work that day.
I think that translates into amplitude.
Left hand and right hand, which one's which? What does that mean?
Yeah, because this is the 4-point amplitude.
Ah, there we go. Perfect. So it's the 4-point. It's not quite the 4-point amplitude because the 4-point amplitude has to conserve momentum. This thing here doesn't conserve momentum, but you're right in that this is the reason why I did this, because this thing will allow me to later on to see all the nice factorization properties of QCD. So this thing here is actually what you would get from the iconal factor in the soft limit, and for this process, that's all there is. But this thing here gives us the right factorization, the soft limit, and this thing here is setting up the tree level amplitude that it wants to factorize onto whenever P5 becomes unresolved. So that was why I wrote that. That's a nice way. All right, good. How are we doing? Good, half an hour left. All right.
I feel like yesterday you used a couple times, you canceled things where it had to be that 4, 5 equals 5, 4. Would you like to track that to 4, 5 squared in denominator?
Well, I wouldn't. Oh, this isn't. Hang on. This is. No, that's bad. This should be a 3, 5.
Okay.
That was. I could have done if that wasn't. If I'd meant what I'd written, that would be a good thing to do. But that would have been devastating because then I would have a very nasty pole in my amplitude which broke all of QCD. All right. Good. Okay. So now. Okay. So we can argue about whether that was simpler than doing a Feynman diagram calculation. Arguing is always fun. But what we can certainly see was that it was nice and algebraic, right? I have my amplitudes, which were my ingredients. I just shoved them into my recursion relation. I put in my shift. I got the answer. If I was feeling very hard working, I could then take another shift. There's not so many to choose from here, but I could try to calculate it a different way and see if I got the same answer, which would indicate I'd done a good job. Or I could move on with my life. Now, okay, we'll add in another gluon just to see how the general relationship works, and then we'll see that by adding in one more, we actually already get to the level where we could calculate an endpoint amplitude. So calculating an infinite number of Feynman diagrams is very hard, but calculating, well, not infinite, but let's say n is equal to 20 million is very hard, but calculating from the recursion relation is very easy. So we're going to calculate 20 million gluons added on with this QQ bar. So E plus E minus to QQ bar plus 20 million gluons. All right. So how are we going to do that? We'll do this one first, and then we'll see that we've already done the general result. So, yes?
How do you know that you can have, that there is a shift such that d sub k is 0 for all of your things?
So you can certainly look at the form. So what gives you most information is the form of the 3-point vertex.
Okay.
So you have like GGG, QQG, and you can put that in and then work out. So you have different helicity options for each one, right? So for example, if you have plus plus, minus minus minus, minus, you can classify all the different helicity pairings, and then you can put in the Feynman rules and then put analytically in the shift and try to work out whether it's got large Z behavior from that alone. So for gluons, for pure gluons, you can actually classify exactly which shifts give you good and bad shifts. And then in a more abstract theory, there's something you have to sit down and work out from your 3-point vertices what your good shifts would be. So you can, with some time and effort, work out what shifts you would expect to work. Yes?
Are we assuming that there aren't any contact interactions or anything like that?
I'm assuming that this is the joy of this method, because all I really need is a Lagrangian to give me a 3-point amplitude, and then I can calculate all 3 amplitudes in the spectrum. So if you give me a Lagrangian, I calculate 3-point amplitude, complex momentum. There you go. I'd prefer it if all my final states were massless. All right, good. All right, so we stick on another gluon. So now we're shifting. We're always going to shift the last gluon in color ordering. So here the color ordering is 3, 4, 5, 6. So we go around that way. The 1 and 2 are mislabeled, but they're not colored, so it doesn't matter. And so we're shifting the last gluon and the first negativistic quark. So again, there's only one possible amplitude. You might think there should be 2, right? So if I put the plus gluon here, but then I would have 3 pluses and a minus, and that amplitude vanishes in QCD. So I can't put any more positive gluons. I can't put here. I can only put them here, and that's why it's easy to solve the endpoint recursion relation, right? Because all I'm ever going to do is just add on positivistic gluons here to calculate all the MHV amplitudes in the spectrum. So from now we can this thing is completely general by just adding in more gluons on that side. So that's good. All right, so now we basically go through exactly the same steps. 5 goes to 6 pretty much everywhere, and we would get something which looks like this. So we would get to almost identical place we were a second ago. We get to the spinor sandwich stage, but now we have to be a little bit more careful because we don't have such simple momentum conservation that p hat is trivial. So the reason why we're doing this is that this is the example where you actually see how we have to solve the residue, which is more generic than this warm-up example here. So now this spinner sandwich is a bit more complicated. So 5p hat 3 is 5, 6, 6, 3, which is coming from the unhatted bit of p. And then I get the z-dependent bit, which is 5, 4, 6, 3. So you see there's a 6, 3 that I can factor. And that's going to cancel this 6, 3 in the numerator. And then I'm left with solving for z. So I have to solve for z using my equation that tells me it's minus, this chalk is literally just a nub now. It tells me it's minus p squared divided by j pi. Right, so I use this equation here, which tells me how to calculate my residue. And for my choice, I get that z is 3, 6 over 3, 4. So the square bits cancel. So now when I put this into my amplitude here, the square bracket dependence is gone, so we're already in something which looks MHV. And we just have to tidy up the denominator, and then we're good to go. So what we have left at the moment is 2, 4 squared divided by 1, 2, 3, 6, 4, 5, 3, 6, 4, 5 plus 3, 4, 5, 6. And this thing in the denominator is yuck. We don't like this. But remember that there's the nice Ciaran identity which tells us that we can redistribute this as one term, which will get 3, 4, 5, 6. So we use the Ciaran ID to rewrite the whole thing as 2, 4 squared divided by 1, 2. Then what we've got 3, 4. No, sorry, 3, 4's gone. It's 3, 5. So I get. All right, and so what I get left over with is 2, 4 squared over 1, 2, 4, 5, 5, 6, 6, 3. And you see what we start building up in the denominator are these cyclic, these connected pairings of spinor products. So now we could make a guess of how to solve the endpoint relation, and that would just be 2, 4 squared, 1, 2. So we start with 4, 5, and we go all the way around, 5, 6, all the way around to n, 3 at the end. That's messy. This big chalk is not my friend. So this escalated quickly. A couple of minutes ago, we were just looking at 5-point amplitude, and now we just calculated for any number of additional positivity gluons that we would like. So that shows you that, okay, so I've chosen this nicely because adding in positivity gluons is easy because MHV amplitudes have the nicest structure. So that's sort of cheating, because if I was to do a 20 million gluon amplitude, for an arbitrary helicity, that would be horrendous too. But the point is that you see here that we were able to get this closed form very nice and very quickly. And if we were doing this with Feynman diagrams, this would be yucky. All right. How are we doing? 15. We have a question?
Well, when you're doing the cyclic, so if you're getting 7, so then you have 5, 6, and then you have
6.
9.
So how many gluons do you want to add in? Another one? Do you have a 7th gluon? It would go 5, 6, 6, 7, 7, 3.
Okay.
All right, so just connect back around.
Right, and you're going to repeat it then.
All All right, good. Okay, so that was the end of our discussion of tree level techniques. So we have 15 minutes left before dinner, so I'll just waffle on a little bit about next leading order, then we'll start doing some serious stuff on next leading order tomorrow. All right, so tree level now we can effectively treat as a solved problem. So we have recursion relations that allow us to calculate arbitrary processes, and so we just press a button, MyGraph or Sherpa work very hard to give us the scattering amplitude that we want, and then we plug it into our generator, we calculate distributions, we compare it to data. It's awful. We need to go to one higher order to have any chance of looking anything like the data. So we're going to go to next leading order. So there's two types of topology that we're going to get a next leading order. The next leading order. So here we have some simple Higgs to BB bar decay. So a leading order, we just take the Higgs matrix elements, square it up, and that's what we would have. Now at next leading order, we're going to address it with one additional gluon. So we can connect this gluon two possible ways. We can connect it so this blue dashed line here is the cut, which represents the particle as a physical final state particle. So we could dress our additional radiation so it's on both sides, same side of the cut, and this then isn't a real final state particle. So this is an unobserved particle, so we call this a virtual correction. And we see this is a loop diagram here times a tree level amplitude. And of course that would be the other way around, so we'd have 2 times the real part of this interference. Well, I moved the gluon over here. But schematically, that's where we'd include the loops. Right? This is the virtual corrections. They have loop diagrams in them. Now, I could also take my gluon and dress it across the cut. You see, it's the same order in perturbation theory. Both of them have 2 additional vertices, which gives me a alpha S correction. So here, my diagram here, the gluon crosses the cut. It becomes a real final state particle, which can have observable consequences. So this is called the real momentum, the real amplitude here, right? And so we have different techniques for dealing with different parts of the calculation. But nowadays, next leading order is essentially a solved problem. So now, again, you can go to MyGraph and AMC NLO, all this sort of stuff, and say, okay, I would like to know my LHC process of interest at next leading order accuracy. And they will say, very good, I will work hard behind the scenes and do that for you. Right, so it doesn't require human intervention anymore to calculate something at next leading order accuracy. So we've solved this problem in QCD and indeed the standard model in general. So we can do next leading order lecture a week, next leading order, whatever you like. So how do we do that? So that's what we're going to talk about mostly tomorrow. There's a few complications at next leading order that we have to address, and these then progress onto higher orders. They get even worse. So we have to understand them at next leading order. So there's two types of problems. Which I'm sure you've definitely at least heard of one and probably not heard so much about the other. So the issue is that these things are riddled with divergences, right? So this one over here, this loop diagram, has 2 types of divergence, which we call UV for ultraviolet and IR for infrared. So the UV divergence is probably, it's the better looking cousin. It's the one you've probably studied a lot in your QFT lectures, right? So a UV divergence occurs when the loop momentum is very large, and you have problems with these high scales. And the way you resolve that is by renormalizing the theory. So this is typically very, it's always in the QFT textbooks, it's always well discussed, so I'm going to assume that you know about renormalization. We're not going to talk about that very much. Then the problem at the other end of the spectrum is if the loop momentum is small. So if I have a very soft or collinear exchange such that one of these invariants vanishes, then I get an infrared divergence. And the infrared divergence is tricky for people that would like to make a prediction for LHC physics, because this one, so UV, I sit here, I renormalize, this thing is UV finite, this thing is UV finite, I can move on with my life. Now I do infrared physics, this thing is infrared divergent, and this one is infrared divergent. They're both separately infrared divergent. The only way I have a hope of making something which is a physical prediction is by combining the 2 of them together in a suitably defined way. And so that's the problem that we face, and the reason it's tricky is that we see they're very different processes. So this one here looks like a 2-body process. It's Higgs to BB bar with a loop in one of the amplitudes and a tree level on the other one. This one over here looks like Higgs to 3 partons squared. So one of them has 2 partons in the final state, the other one has 3. So when we're writing a code to generate these things as distributions, this thing has a completely different phase-space dimensionality to this one. So we write this as a completely separate Monte Carlo to this, but this thing is blowing up and it's divergent, so this is the answer we get infinity. and this thing over here is also divergent, so we get infinity too. So that's not very useful. So we need some way of handling the infrared divergences such that both of these are going to be able to be calculated separately and then combined together at the end to make something sensible. So that's going to be the aim of tomorrow's lecture. All right, so we'll start briefly talking about the loop stuff before dinner. Does anyone have any questions on this slide? No? Okay, good. So the nice thing about one loop is that we have a basis. So any one loop amplitude can be written in the following basis, where we sum over all possible ways of assigning the external legs to a box topology. So we have 4 loop propagators, a triangle topology with 3, bubbles with 2, and then this mysterious leftover R, which is a rational function in the external momentum. So in these coefficients, D, C, and B, they depend only on the external kinematics, and they don't depend on the loop momentum, and they're rational functions too. And then these loop functions are just all possible ways I can assign my legs to make a box, or vice versa, right? So that's that at first glance is quite remarkable. It's probably why you wouldn't guess, because if I had 5 particles in the final state, you're going to get a pentagon-type Feynman diagram, right? Where I have a pentagon shape. And so you would expect there to be a pentagon in this, because I need to understand what's going to happen to the pentagon Feynman loop. So this was proven in the mid-90s, and the proof is way beyond the scope of this lecture. If you're interested, I'll give you the reference in the notes. But this was showing that actually you can always reduce these pentagons and heptagons and or whatever n-gons you want to worry about into this basis, right? Which is nice. This gives us, so this is going to make, this is essentially what gives us a very doable way of solving one loop. So there's caveats. There's always small print. So the small print here is that I've assumed that my final states are massless. What would be the difference if I didn't assume they are massless? Well, I'd have tadpoles, because I can have single propagator integrals, which depend on the mass. That's not a big deal. The other thing I've implicitly assumed is that I'm in the 4-dimensional helicity scheme, so that all my final states are 4-dimensional. Right? This thing here is only accurate to there's corrections to this thing that go like order epsilon, where epsilon is my regulating parameter in d dimensions. And so this result is not true for full general dimensions, but is true when I expand around 4 dimensions. If I wanted to have a result that I could expand to any order in epsilon, if I really wanted to feel like I'd done a good job, then I can use a different basis, which is slightly more complicated, but nevertheless exists. And that one does have pentagons. So that one has pentagons, boxes, triangles, bubbles, and no rational term, but it also has then some 6-dimensional triangles and bubbles and boxes and an 8-dimensional box. So a slightly more complicated basis, but nevertheless a basis. Yes? It has, it can have any number of external legs you'd like that are, so if they're massless, it has to have at least 4. It's because this has to be a mass and this has to be a mass. But if I had one massive leg here, then that would allow me to have 3, right? So yeah, but it has to, yeah. So I can address this either way, right? Yes.
You were saying that this is only necessarily true in 4 dimensions.
This is only true for 4-dimensional final states.
Yes. Well, I guess that's my point here is that unless you're dealing with string theory or another higher dimensional theory, I can't think of any, like in conventional QCD, which we normally assume we're in a 4-dimensional world. How would you?
Okay, so I have to reverse the bus a little bit. So when I do a loop integral, I'm going to do it in d dimensions, right? So to regulate my divergences. So I'm calculating QCD in d dimensions. Now I have a choice in how whether I do everybody in d dimensions, so loop momenta and external legs. So that's what's called conventional dimensional regularization, where I say, guess what, I'm working in d dimensions, not 4. Compute everything, right? That's some way the best, because then there's no confusion about who lives in what state. But I could be then slightly more intrepid and say, well, I know the physical states are always going to be 4-dimensional, so I don't bother putting them in d dimensions, and I only keep the unresolved emissions that correspond to the loop in d dimensions. And that's what this formula is assuming here, that these are 4-dimensional, and the bold ones are d-dimensional. So this box, the loop propagator is d-dimensional, and this triangle is d-dimensional too. All right. Any other questions? Yes?
So I can imagine as hard as there's some way to understand, morally speaking, why the benefit of hindsight
Yeah, you can. Yeah, that's a good question. So you basically, because we live in this four-dimensional world and we're always expanding around 4 dimensions, that you can. We'll see that we are going to solve these for these coefficients by putting in the loop dimension as 4-dimensional plus some correction, right? And that correction is effectively what you write things in terms of. So you have some 4 degrees of freedom plus higher dimensional correction. That higher dimensional correction is essentially what generates these rational terms here, and that's why the pentagon is really absorbed in some box-like configuration plus a rational correction. So that's the. After that, it's just math. All right. Good. Okay. So all right. I don't really want to start unitarity with 5 minutes to go. So I guess we will finish 5 minutes early, and then I would go 5 minutes late tomorrow. So anyone has any other questions? All right, so tomorrow we're going to look at how you calculate these coefficients. What we're going to do is effectively do a divide and conquer approach, where we just calculate each one of these things individually. It's super simple. And so the way we're going to calculate them individually is by using a specific method called unitarity, which allows us to isolate the coefficients of each scalar integral. And that's tomorrow what we'll address. Okay, so I don't want to start that now because it's late, but if there's any questions, feel free. If not, I'll have an early dinner, and like I say, I've got 10 minutes on the clock for tomorrow. All right, see you then.